Hello, this is Dr. Daystorms, and today we're going to begin our first PowerPoint in Chapter 4, which has to do with aqueous solutions. And to begin with, we're going to talk about how aqueous solutions form, and also discuss electrolytes versus non-electrolytes. So let's go ahead and get started. First off, if we review from the beginning of the semester, we have the homogeneous versus a heterogeneous mixture. A mixture is whenever we have two or more substances that are combined together. If it's homogeneous, it means it's mixed the same throughout. So whether you take a sample from the top or from the bottom, it's going to have the same concentration of the ratio of the components. Whereas if it's heterogeneous, it's not. For example, sand in water would be heterogeneous, whereas salt water is homogeneous. However, whenever we have a homogeneous mixture, one of the components is going to be in a higher quantity than the other components. Whichever component is in the greatest amount is called the solvent. Anything else is called the solute. The solvent and the solute together makes up what's called the solution. So in our example with salt, for example, if we take 10 grams of sodium chloride, which is table salt, and we add that to 1 liter of water, in fact I'll say distilled water, we would have the solvent would be the water, and the solute would be the sodium chloride, because it's in a smaller amount. In this picture here, we have a solution of copper nitrate. And so copper nitrate, even though it's brightly blue, you have a small amount of copper nitrate that's dissolved in water. So water again would be the solvent, and the copper nitrate is the solute. I've already used this term about how sodium chloride, for example, or the copper nitrate, dissociates in water. And the way that happens is that the water molecules come across and pull off the cations and the anions. Because if you remember, these were ionic bonds. And so if we first want to review, let's review the types of bonding that we've talked about already. We had ionic bonds. Whoops, let me change this to red. We had ionic bonds or ionic interactions for ionic compounds, which was where we had a metal cation, something like sodium, lithium, or ammonium. So they're positively charged. That binds to a negatively charged non-metal cation, or, non-metal anion. I'm sorry about that. Or a polyatomic anion. So the non-metal anions were like fluoride, bromide, oxide, and the polyatomic anion would be like sulfate, phosphate, carbonate. Then we had molecules, which were molecular interactions. These are covalent. That's where the electrons are shared between the atoms. And so these were between nonmetals, typically. So things like sugar, you could also have methane, carbon dioxide, carbon monoxide, tetraphosphorus decoxide, things like that. So let's go back to dissociation. Things that are ionic many times can dissociate in water. Not always. We'll talk about some exceptions in a moment. And when I say something is soluble, that means that it dissociates. And in this class, we typically refer to things being soluble. We're talking about water solubility. So if we have something like sodium chloride that can completely dissociate in water, many times we call that an electrolyte, because it dissociates into the ions when dissolved in water, and it can conduct electricity. Whereas there are certain things that are called non-electrolytes because they may dissolve in water, for example sugar, but it doesn't conduct electricity and it doesn't break apart into ions because it was a molecule. So perhaps this little video can explain it.
We know from various lines of experimental evidence that solid sodium chloride consists of an ordered three-dimensional array of sodium and chloride ions. Solid sodium chloride is not a conductor of electricity. The ions of the ionic lattice are held in place by the strong ionic interactions in the solid and therefore are not free to move under the influence of the electric field. When sodium chloride is dissolved in water, it forms a solution of separated sodium and chloride ions. The presence of ions in the solution is responsible for the fact that the solution is a conductor of electricity. Substances such as sodium chloride that exist in aqueous solution entirely or nearly entirely as ions are called strong electrolytes. By contrast, an aqueous solution of a non-electrolyte such as sugar does not conduct electricity.
Hopefully that helps explain a little bit about electrolytes versus non-electrolytes. So once again, soluble ionic compounds tend to be electrolytes. There are some exceptions. Okay? Whereas, or I should say, if they're soluble ionic compounds, then they're going to be an electrolyte. They tend to be strong electrolytes. If they're insoluble, then they won't be an electrolyte at all. Whereas molecular compounds, only if they're strong acids or bases do they tend to be strong electrolytes. Otherwise, many of them are going to be weak acids or bases or weak electrolytes, or they'll be non-electrolytes completely, such as sugar and carbon dioxide. So a strong electrolyte dissociates completely when dissolved in water. A weak electrolyte only dissociates partially when dissolved in water. So what are the strong electrolytes? You need to memorize 7 strong acids. Okay? These are 3 of the halogens, hydrochloric, hydrobromic acid, and hydroiodic acid. Please note, hydrofluoric acid is not a strong acid. Then we have chloric and perchloric acid, nitric and sulfuric acid. So in Gen Chem, those are our 7 strong acids. Then we have our strong bases. Any of the group 1, that's the first column, metal hydroxides. So lithium, sodium, potassium, rubidium, cesium, and in theory, francium hydroxide. And then the strong bases from calcium on down from the group 2, the alkali earth metals. So calcium hydroxide, strontium hydroxide, and barium hydroxide. Then we have our soluble ionic salts. This table here can be a little confusing at times, and so I want to take some time to explain it. First off, you need to look at the anion to determine whether the ionic compound is going to be soluble in water or insoluble in water. Let's start with the soluble ones. The easiest are nitrates and acetates because there are no exceptions. So anything that's a nitrate or acetate is going to be soluble. Also, chloride, bromide, and iodide salts are going to be soluble, except if it's with silver, mercury, or lead too. Finally, anything that has a sulfate will be soluble except for strontium, barium, mercury, and lead. And you just have to memorize the exceptions. Whereas, if there are certain anions that tend to be insoluble. So, all of the sulfides, those are the ones that just end in S, are going to be insoluble except for ammonium, anything from the group 1, so that alkali metals, and calcium, strontium, and barium. Those sulfides will be soluble. They will dissolve in water. Likewise, anything that's a carbonate will be insoluble except for ammonium and the group 1 metal cations. The same is true for phosphate. So if you notice, phosphate and carbonate are identical here. Phosphates and carbonates tend to be insoluble in water unless they are paired with ammonium or the alkali metals, the cations from the first column of the periodic table. Finally, the hydroxides are insoluble unless it's from group 1 on the periodic table, ammonium, calcium, strontium, or barium. Then they are soluble in water. So I hope that this has helped explain a little bit about solubility or dissociation of ions and what electrolytes versus non-electrolytes are. I hope to see you in class soon.